Welcome viewers. I am Uma Maheshwari, AP Triple Department, RMD Engineering College. This session I am going to introduce about the Unit 2 in the subject Power Electronics. Subject code is E8552. The session topic is Phase Control Rectifier. What is a rectifier? So rectifier is a device which converts fixed AC into variable DC is known as control rectifiers. So we are able to obtain a variable output voltage, controlled output voltage. Such a rectifier is known as controlled rectifier. So a type of rectifier whose output voltage can be varied or changed is called as controlled rectifier. Now, what is phase control? By varying the firing angle alpha, the alpha is known as represented by the firing angle is represented by the term alpha. The phase relationship between the start of the load current and the supply voltage can be controlled. So, hence the term phase control is used in this method of controlling the load current. So here, with by varying the delay angle or firing angle, we are able to change the relationship between the load current and the supply voltage waveform. This method of control is known as phase control. What is firing angle definition? The firing angle is defined as the angle measured from the instant the SCR gets forward biased to the instant it is triggered. So SCR is forward biased once it is get forward voltage is applied to it. What is forward voltage applied to an SCR? Anode connected to positive, cathode connected to negative, and a positive voltage is applied, forward voltage is applied. Then this SCR is said to be forward biased. So the instant, the angle measured from the instant, the SCR gets forward biased to the instant it is triggered. Trigger means a delay angle or firing angle is given to the SCR. So this difference is known as delay angle or firing angle. It is represented by the symbol alpha. Now we will discuss about the single phase half wave thyristor circuit for R load. Okay, single phase half wave thyristor circuit for R load. So this is the circuit diagram for single phase half wave thyristor circuit. So here you can see the supply voltage. It is represented by Vs, which is equal to Vm sine of omega t, and the supply voltage is connected to a thyristor, and the voltage across the thyristor is represented as Vt, and the resistive load is connected, and this resistive load is represented by R, and the voltage across the resistive load is represented as V naught, and the output current is represented as I naught. So here you can see that the positive of the supply is connected to the anode of the thyristor, and the cathode of the device is connected to the R load. The other end of the load is connected to the negative of the supply waveform. Okay, this is the circuit diagram of single phase half wave circuit. Now we will see the waveform of it. So the positive half cycle of the supply voltage, it is from 0 to pi, and the negative half cycle of the supply voltage, that is from pi to 2 pi. So one complete cycle is this positive half cycle and negative half cycle, and this is the delay angle or firing pulses. It is represented by Ig, gate current. So what is the definition of delay angle or firing pulse, firing angle? It is the instant at which the SCR gets forward biased to the instant the SCR gets triggered. So this difference here at omega t equal to 0 is the instant the SCR is forward biased. A positive voltage is applied to the SCR, and at this instant the SCR gets triggered. So this difference, this angle delay is known as the delay angle or firing angle. It is represented by the notation alpha. Okay, and then we'll see the output voltage waveform discussion. So now the SCR gets turned on only if these two conditions are satisfied. The first condition is the SCR should be forward biased and the gate pulse should be given. If both these conditions are satisfied, the SCR gets turned on. See, at this instant SCR is forward biased at instant 0, whereas the delay angle or firing angle is given at instant alpha. So only after instant alpha the SCR gets turned on. Until that the SCR is in off state. So since the SCR is in off state, here it is the open switch. The SCR acts as an open switch. So no current flow from the source to the load. So the output voltage is 0 from the instant omega t equal to 0 to omega t equal to alpha. At instant alpha, what is happening? The trigger pulse is given to the SCR. Firing pulse is given to the SCR. So already the SCR is forward biased at instant omega t equal to 0. Now trigger pulse is given to SCR at alpha. So the SCR gets turned on. As soon as the SCR turns on, it acts as a closed switch. It acts as a closed switch. Now the power flows from the source to the load through the SCR, and there is a flow of current I naught. So this flow of current and there is an voltage generated across the load. It is represented as V naught. This output voltage will be same as that of the supply voltage. So when we trace the waveform for the output voltage, we trace the same wave shape of the sinusoidal voltage waveform. So this is our voltage waveform from instant alpha to pi, which is same as that of the supply voltage waveform from instant alpha to pi. The waveform it is represented as Vm sine of omega t supply voltage waveform. Whereas at instant alpha, the voltage value is Vm sine of omega. Okay, Vm sine of alpha, Vm sine of alpha. Now at instant pi, what is happening? At instant pi, what is happening? The polarity of the supply waveform reverses. That is the negative half cycle. So during the negative half cycle, the phase terminal is negative and the neutral terminal is positive. The polarity interchanges. Now, the negative of the supply is given to the anode of the thyristor, and similarly, the positive of the supply through the load is connected to the cathode of the thyristor, which means that the thyristor is reversed biased. So, once the thyristor is reverse biased, it turns off. And here, since it is an R load, the current I0 also vanishes to 0 at this instant pi. So since there is no current through the thyristor and the thyristor is reverse biased, the thyristor stops conduction. So the output voltage is 0 from the instant pi to 2 pi. So this way of commutation of the thyristor by the natural reversal of the supply voltage waveform is known as line commutation. Okay, so thus the thyristor is turned off by line commutation at instant pi, and the output voltage across the load is 0. So once the thyristor is reverse biased, it acts as an open switch. So there is no power flow from the source to the load because it is an open switch here, and the output voltage is 0. It is 0 from instant pi to 2 pi. Okay, so here you can see that the output current is also 0 from pi to 2 pi. Okay, now we'll discuss about the instant 2 pi. What is happening at the instant 2 pi? At 2 pi, the cycle repeats. Okay, the thyristor T1 is forward biased, whereas it is given trigger pulse only at instant pi plus alpha. This is your instant pi plus alpha. So the SM 2 pi plus alpha. So the SCR gets turned off only at the instant 2 pi plus alpha. And the output voltage waveform resembles same waveform as that of the supply voltage. And the output current is Vm by R. Whenever SCR is conducting, the output voltage is Vm by R. Okay. So this is our output voltage waveform and output current waveform discussion. Now about the voltage across the thyristor. So from the instant, we start discussion from 0. From the instant 0 to alpha, is the SCR conducting? No, the SCR is not conducting. It is in forward bias condition, whereas gate pulse is not given. So SCR is not conducting. So whenever SCR is not conducting, it will block the applied voltage. What is the voltage applied to this SCR at this instant 0 to alpha? It is this positive supply voltage is applied. So here you can see that it is blocking the applied positive voltage. Okay, and from instant alpha to pi, SCR is conducting. So assuming that the SCR is ideal device and there is no loss when it is conducting. So here you can see that whenever device is conducting, the voltage across the device is 0. Okay, so assuming the SCR is ideal, we are assuming there is no loss and the voltage across the device is 0. So this is from instant alpha to pi. And after instant pi to 2 pi, what is happening? The SCR is in off state, output voltage is 0. So SCR is blocking the applied reverse voltage. Whatever reverse voltage applied here, it is blocking the applied voltage. So the entire reverse voltage is appearing across the SCR. So it is the waveform is this. and this continues until the instant 2 pi. The SAR is blocking the applied voltage. So the repetition of the cycle takes place. So this is about the single phase half wave rectifier circuit diagram and the waveform explanation. Now we will go to the average output voltage. Okay, so V output is equal to 1 by 2 pi integral of alpha 2 pi Bm sine of omega t d omega t. So 1 by 2 pi, what is this? 1 by 2 pi, 1 by base period. So the base period is 2 pi. After 2 pi, the repetition of the waveform is taking place. So we are writing it is base period as 1 by 2 pi. And you can see the output voltage waveform, it is from alpha to pi, it is Bm sine of omega t. So we are integrating from alpha 2 pi Vm sine of omega t d omega t. So this Vm is taken common now divided by 2 pi, and integration of sine omega t is minus cos of omega t, and we are substituting the limits alpha and pi. Upper limit is pi and lower limit is alpha. So when you are substituting the limit, it is upper limit minus lower limit. So this Vm by 2 pi is written as such. In substitution of the limit, it is minus cos of pi, minus into minus plus cos of alpha. So cos of pi is nothing but minus 1. So this minus into this minus, it becomes plus 1, and cos of alpha is written as such. So the output voltage expression for single phase half wave rectifier circuit V output is equal to Vm by 2 pi 1 plus cos of alpha. And when we are able to obtain the maximum average output voltages when the delay angle is 0. So substituting alpha equal to 0, we are obtaining the maximum voltage here as Vm by pi. And the average load current I naught is equal to V naught by R. We know the V naught expression, it is Vm by 2 pi into 1 plus cos of alpha divided by R gives you the value of I naught. So it is Vm by 2 pi R 1 plus cos of alpha. Thank you all.